Welcome to 6851, Advanced Data Structures. I am Erik Demaine. You can call me Erik. We have two TAs, Tom Morgan and Justin Zong. Tom's back there. Justin is late. And this class is about all kinds of very cool data structures. You should have already seen basic data structures like balanced binary search trees and things like that. Log n time to do whatever you want in one dimension. And here we're going to turn all those data structures on their head and consider them in all sorts of different models and additional cool problems. Today we're going to talk about time travel or temporal data structures, where you're manipulating time, as any good time traveler should. Then we'll do geometry, where we have higher dimensional data, more than one dimension. Then we'll look at a problem called dynamic optimality, which is there one best binary search tree that rules them all? Then we'll look at something called memory hierarchy, which is a way to model more realistic computers, which have cache, and then more cache, and then main memory, and then disk, and all these different levels. How do you optimize for that? Hashing is probably the most famous and most popular, most used data structure in computer science. We'll do a little bit on that. Integers. When you know that your data is integers and not just arbitrary black boxes that you can compare or do whatever, you can do a lot better with integers, usually beat log n time. Often you can get constant time. For example, if you want to do priority queues, you can do square root log n time. That's the best known. Randomized. Dynamic graphs, you have a graph you want to store and the edges are being added and maybe deleted. Like you're representing a social network and people are friending and defriending. You want to maintain some interesting information about that graph. Strings, you have a piece of text such as the entire World Wide Web, and you want to search for a substring. How do you do that efficiently? It's sort of the Google problem, or you're searching through DNA for patterns, whatever. And finally, succinct data structures, which is all about taking what we normally consider optimal space, order n space, and reducing it down to the very bare minimum of bits of space. Usually, if you want to store something where there's 2 to the n possibilities, you want to get away with n bits of space, maybe plus square root of n, or something very tiny. So that's succinct data structures. So that's an overview of the entire class, and these are sort of the sections we'll be following. Let me give you a quick administrative overview of what we're doing. Requirements for the class, I guess first, attending lecture. Obviously, if you don't attend lecture, there'll be videos online, so that's resolvable, but let me know if you're not going to make it. We're going to have problem sets roughly every week if you're taking a class for credit. They have a very simple rule of 1 page in, 1 page out. This is more constraint on us to write problems that have easy or short answers. You probably need to think about them a little bit before they're transparent, but then easy to write up. And then scribing lectures. So we have a scribe for today, I hope. Here? Yes, good. So in most of the lectures have already been scribed in some version, and your goal is to revise that scribe notes so that if you don't like handwritten notes, which are also online, then easier for people to read. Let's see. Listeners, welcome. We're going to have an open problem session. I really like open problems. I really like solving open problems, so we've done this every time this class has been offered. So if you're interested in also solving open problems, it's optional. We'll organize in a couple of weeks. We'll have a weekly open problem session and try to solve all the things that push the frontier of advanced data structures. So in classes, we'll see the state of the art, and then we'll change the state of the art in those sessions. I think that's it. Any questions about the class before we get into the fun stuff? All right, let's do some time traveling. Before I get to time traveling, though, I need to define our model of computation. A theme in this class is that the model of computation you're working with matters. Models matter. And there's lots of different models of computation. We'll see a few of the main ones in this class. And the starting point, and the one we'll be using throughout today, is called a pointer machine. It's an old one from the 80s. And it corresponds to what you might think about if you've done a lot of object-oriented programming. And before that, structure-oriented programming, I guess. So you have a bunch of nodes. They have some fields in them, constant number of fields. You can think of these as objects or structs in C, or used to be records back in Pascal days, so a lot of the papers call them records. We just have a constant number of fields. You could think of them as numbered, labeled. Doesn't really matter because there's only a constant number of them. Each of the fields could be a pointer to another node, could be a null pointer, or it could have some data in it. So I'll just assume that all my data is integers. I don't know, you can have a pointer to yourself. You can have a pointer over here, whatever you want. That's a pointer machine would look something like this. And in any moment, this is the state of the pointer machine. So you think of this as what the memory of your computer is storing. And then you have some operations that you're allowed to do. That's the computation part of the model. You could think of this as the memory model. What you're allowed to do are create nodes. So you can say something like x equals new node. You can, I don't know, look at fields. So you can do x equals y dot field. You can set fields, x dot field equals y. You can compute on these data, so you could like add 5 and 7, do things like that. I'm not going to worry about, I'll just write etc. This is more a model about how everything's organized in memory, not so much about what you're allowed to do to the data items. In this lecture, it won't matter what you're doing to the data items. We never touch them. We just copy them around. So, am I missing anything? Probably. I guess you could destroy nodes if you felt like it, but we won't have to today because we don't want to throw anything away when you're time traveling. It's too dangerous. And then the one catch here is what are x and y? There's going to be one node in this data structure or in your memory called the root node. And you can think of that as that's the thing you always have in your head. This is like your cache, if you will. It's just got a constant number of things, just like any other node. And x and y are fields of the root. So that sort of ties things down. You're always working relative to the root, but you can look at the data, basically follow this pointer by looking at the field. You could set one of these pointers. I think I probably need another operation here, like x equals y dot field 1, field 2, that sort of thing. And maybe the reverse. But you can manipulate all nodes sort of via the root. It's the idea. You follow pointers, do whatever. So pretty obvious, slightly annoying to write down formally, but that is pointer machine. And what we're going to be talking about today in time travel is suppose someone gives me a pointer machine data structure. For example, balanced binary search tree, linked list. I mean, a lot of data structures, especially classic data structures, follow pointer machine model. What we'd like to do is transform that data structure and make a new pointer machine data structure that does extra cool things, namely travel through time. So that's what we're going to do. There's two senses of time travel or temporal data structures that we're going to cover in this class. The one for today is called persistence, where you don't forget anything, like an elephant. And the other one is retroactivity. Persistence will be today. Retroactivity is next class. Basically, these correspond to two models of time travel. Persistence is the branching universe time travel model, where if you make a change in the past, you get a new universe. You never destroy old universes. Retroactivity is more like Back to the Future, where you go back, make a change, and then you can return to the present and see what happened. This is a lot harder to do, and we'll work on that next class. Persistence is what we will do today. So, persistence. The general idea of persistence is to remember everything. Or the general goal, I'd say. And by everything, I mean different versions of the data structure. So you're doing data structures in general. We have update operations and query operations. I'm mainly concerned about updates here. every time you do an update, you think of it as taking a version of the data structure and making a new one. And you never want to destroy old versions. So even though an update, like an insert or something, changes the data structure, we want to remember that past state as well. And then, to make this reasonable, all data structure operations are relative to a specified version. So an update makes and returns a new version. So when you do an insert, you specify an a version of your data structure and the thing you want to insert, and the output is a new version. So then you could insert into that new version, keep going, or maybe go back to the old version, modify that. I haven't said exactly what's allowed here, but this is sort of the general goal. And then there are 4 levels of persistence that you might want to get. First level is called partial persistence. This is the easiest to obtain. And in partial persistence, you're only allowed to update the latest version, which means the versions are linearly ordered. This is the easiest to think about. Time travel can easily get confusing. So start simple. We have a timeline, various versions on it. This is the latest. And what we can do is update that version. We'll get a new version, and then our latest is this one. What this allows is looking back at the past to an old version and querying that version. So you can still ask questions about the old version. You want to be able to do a search in any of these data structures, but you can't change them. You can only change the most recent version. So that's nice. It's kind of like Time Machine on Mac, I guess. It's like if you've ever seen the movie Deja Vu, which is not very common, but it's a good time travel movie. In the first half of the movie, all they can do is look back at the past. Later, they discover that actually they have a full persistence model. It takes a while for dramatic effect. In full persistence, you can update anything you want. So, update any version. And so then the versions form a tree. Okay, so in this model, maybe you initially have a nice line of versions, but now if I go back to this version and update it, I branch, get a new version here. And then I might keep modifying that version sometimes. Any of these guys can branch. So this is why I call it the branching universe model. When you update, you branch. So no version ever gets destroyed here. Again, you can query all versions, but now you can also update any version, but you just make a new version. It's a totally new world. When I update this version knows nothing about doesn't know about this future. It's created its own future. And there's no way to sort of merge those universes together. It's kind of sad. That's why we have the 3rd level of persistence, which lets us merge timelines. It's great for lots of fiction out there. If you've seen the old TV show Sliders, that would be confluent persistence. So confluent persistence, you can combine 2 versions. To create a new version. And in this case, again, you can't destroy old versions. In persistence, you never destroy versions. So now the versions form a DAG, a directed acyclic graph. So now we're allowing, okay, you make some changes, whatever, you branch your universe, make some changes. And now I can say, okay, take this version of the data structure and this version and recombine them. Get a new version, and then maybe make some more changes. Okay, what does combine mean? Well, it depends on your data structure. A lot of data structures have combine operations, like if you have linked lists, you have two linked lists, you can concatenate them. That's an easy operation. Even if you have binary search trees, you can concatenate them reasonably easy and combine it into one big binary search tree. So if your data structure has an operation that takes as input two data structures, then what we're saying is now it can take two versions, which is more general. So I could take the same data structure, make some changes in one way, separately make some changes in a different way, and then try to concatenate them or do something crazy. This is hard to do, and most of it is an open problem, whether it can be done. But I'll tell you about it. Then there's another level, even more than confluent persistence. This is hard to interpret in the time travel world, but it would be functional data structures. If you've ever programmed in a functional programming language, it's a little bit annoying from an algorithm's perspective because it constrains you to work in a purely functional world. You can never modify anything. Okay, now we don't want to modify versions, that's fine, but in a functional data structure you're not allowed to modify any nodes ever. All you can do is make new nodes. This is constraining, and it's you can't always get optimal running times in the functional world, but if you can get a functional data structure, you have all these things because you can't destroy anything. If you can't destroy nodes, then in particular you can't destroy versions. And all of these things just work for free. And so a bunch of special cases are known, interesting special cases like search trees you can do in the functional world, and that makes all of these things easy. So the rest of this lecture is going to be general techniques for doing partial full persistence, what we know about confluent, and what we know about functional. Brief overview. Any questions about those goals, problem definitions? Yeah.
I'm still confused about functional because
What does functional mean?
don't change the data structure. It's creating
Yeah, I guess you'll see what functional looks like all the other things, I agree. You'll see in a moment how we actually implement partial and full persistence. We're going to be changing nodes a lot. As long as we still represent the same data in the old versions, we don't have to represent it in the same way. That lets us do things more efficiently. Whereas in functional, you have to represent all the old versions in exactly the way you used to represent them. Here we can kind of mangle things around and it makes things faster. Yeah, good question. So it seems almost the same, but it's nodes versus versions. I haven't really defined a version, but it's just that all the queries answer the same way. That's what you need for persistence. Other questions? All right. Well, let's do some real data structures. We start with partial persistence. This is the easiest. But for both partial and full persistence, there is the following result. Any pointer machine data structure one catch with a constant number of pointers to any node. So this is constant in degree. In a pointer machine, you always have a constant number of pointers out of a node at most. But for this result to hold, we also need a constant number of pointers into any node. So this is an extra constraint. Can be transformed into another data structure that is partially persistent and does all the things it used to do. So I'll just say it can be made partially persistent. You have to pay something, but you have to pay very little. Constant amortized factor overhead, so multiplicative overhead. and constant amount of additive space per change in the data structure. So every time you do a modification in your pointer machine, you set one of the fields to something, you have to store that forever. So, I mean, this is the best you could hope to do. Got to store everything that happened. Pay a constant factor overhead. We're theoreticians, that doesn't matter. Then you get any data structure in this world can be made partially persistent. So that's nice. Let's prove it. Okay, the idea is pretty simple. The pointer machines are all about nodes and fields, so we just need to simulate whatever the data structure is doing to those nodes and fields in a way that we don't lose old information, and we can still search it very quickly. First idea is to store back pointers. And this is why we need the constant in degree constraint. So if we have a node, how do I want to draw a node here? So I've been drawing, so maybe these are the 3 fields of the node. I want to also store some back pointers. This is whenever there is a node that points to this node, I want to have a back pointer that points back. So I know where all the pointers came from. If there's only p pointers, then this is fine. There'll be p fields here. So still constant, still in the pointer machine model. Okay, I'm going to need some other stuff too. So this is a simple thing. Definitely want this. Because if my nodes ever move around, I've got to update the pointers to them. And where are those pointers? Well, the back pointers tell you where they are. Okay, all nodes will still be constant size. Remain a pointer machine data structure. Okay, that's idea 1. Idea 2 is this part. This is going to store something called mods. Could stand for something, but I'll leave it as mods. So these are to the fields of the data structure. One convenience here is for back pointers, I'm only going to store it for the latest version of the data structure. Sorry, I forgot about that. We'll come back to that later. Then the idea is to store these modifications. How many modifications? Let's say up to p, twice p. P was the bound on the in degree of a node. So I'm going to allow 2p modifications over here. And what's a modification look like? It's going to consist of 3 things. Get them in the right order. The version in which something was changed, the field that got changed, and the value it got changed to. Okay, so the idea is that these are the fields here. We're not going to touch those. Once they're set to something, or whatever they are initially, they will stay that way. And so instead of actually changing things like the data structure normally would, we're just going to add modifications here to say, oh, well, at this time, this field changed to the value 5, and then later on, it changed to the value 7, and then later on, this one changed to the value 23, whatever. Okay, so that's what they'll look like. There's a limit to how many, we can only store a constant number of mods to each node, and our constant will be 2p. Okay, those are the ideas, and now it's just a matter of making this all work and analyzing that it's constant amortized overhead. So first thing is, if you want to read a field, how would I read a field? This is really easy. You just first you look at what the field is in the node itself, but then it might have been changed. And so remember, when I say read the field, I actually mean, well, I'm given some version, v. I want to know what is the value of this field at version v, because I want to be able to look at any of the old data structures too. So this would be at version v. I just look through all the modifications. There's constantly many, so it takes constant time to just flip through them and say, well, what changes have happened up to version v? So I look at mods with version less than or equal to v. That will be all the changes that happened up to this point. I see, did this field change? I look at the latest one. That will be how I read the field of the node. So constant time. There's lots of ways to make this efficient in practice, but for our purposes, it doesn't matter. It's constant. The hard part is, how do you change a field? Because there might not be any room in the mod structure. So to modify, say we want to set node.field equal to x. What we do is, first we check, is there any space in the mod structure? If there's any blank mods, so if the node is not full, we just add a mod. So a mod will look like now field x. Just throw that in there, because right at this moment, so we maintain a time counter, just increment it every time we do a change. This field changed that value. So that's the easy case. The trouble, of course, is if the node is full. The moment you've all been waiting for. So what we're going to do here is make a new node. We've ran out of space. So we need to make a new node. We're not going to touch the old node, just going to let it sit. It still maintains all those old versions. Now we want a new node that represents the latest and greatest of this node. Okay, so make a new node. I'll call it node prime to distinguish from node, where with all the mods and this modification in particular applied. Okay, so we make a new version of this node. It's going to have some different fields, whatever was the latest version represented by those mods. It's still going to have back pointers, so we have to maintain all those back pointers. And now the mods initially is going to be empty, because we just applied them all. So this new node doesn't have any recent mods. Old node represents the old versions. This node has got to represent the new versions. What's wrong with this picture? Update pointers. Yeah, there's pointers to the old version of the node, which are fine for the old versions of the data structure, but for the latest version of the data structure, this node has moved to this new location. So if there are any old pointers to that node, we've got to update them in the current version. We have to update them to point to this node instead. The old versions are fine, but the new version is in trouble. Other questions? All the same answer. Yeah.
So how would you read, if you wanted to read an old version, but you just have like the node, like the new version in hand, you still need to have sort of a back pointer to say,
okay,
beyond this version, you need to go.
Question is essentially, how do we hold on to versions? Essentially, you can think of a version of the data structure as where the root node is. That's probably the easiest. I mean, in general, we're representing versions by a number v. But we always start at the root. And so you start at you're given the data structure, which is represented by the root node, and you say, search for the value 5. Is it in this binary search tree or whatever? And then you just start navigating from the root, but you know I'm in version 1,000,000 or whatever. I know what version I'm looking for. So you start with the root, which never changes, let's say. And then you follow pointers that essentially tell you for that version where you should be going. I guess at the root version, it's a little trickier. You probably want a little array that says, for this version, here's the root node. But that's a special case. Yeah, another question?
In the new node that you created, the fields that you've copied, you also
These
Or do you version the whole node?
here we're versioning the whole node. The original field values represent what was originally there whenever this node was created. Then the mods specify what time the fields change. So I don't think we need times here. All right. So we've got to update two kinds of pointers. There's regular pointers which live in the fields, which are things pointing to the node. But then there's also back pointers, because if this is a pointer to a node, then there'll be a back pointer back to the node, and all of those have to change. Conveniently, the back pointers are easy. So if they're back pointers to the node, we change them to the node prime. How do we find the back pointers? Well, we just follow all the pointers, and then there will be back pointers there. Because I said we're only maintaining back pointers for the latest version, I don't need to preserve them preserve the old versions of those back pointers. So I just go in and I change them. This takes constant time because there's a constant number of things I point to. Each one has a back pointer. So this is cheap. There's no persistence here. That's an advantage of partial persistence. The hard part is updating the pointers, because those live in fields. I need to remember the old versions of those fields, and that we do recursively. Because to change those pointers, that's a field update. That's something exactly of this form. So that's the same operation, but on a different node. So I just do that. I claim this is good. That's the end of the algorithm. Now we need to analyze it. How do we analyze it? Any guesses? Amortized analysis, exactly the answer I was looking for. Okay, shall know amortization. The most powerful technique in amortization is probably the potential method. So we're going to use that. There's a sort of more, you'll see a charging argument in a moment. But we want the potential function to represent when this data structure is in a bad state. Intuitively, it's in a bad state when a lot of nodes are full, because then as soon as you make a change in them, they will burst, and you have to do all this crazy recursion and stuff. This case is nice and cheap. We just add a modification, constant time. This case, not so nice, because we recurse, and then that's going to cause more recursions, and all sorts of chaos could happen. So there's probably a few different potential functions that would work here. In an old version of these nodes, I said should be the number of full nodes. But I think we can make life a little bit easier by the following. Basically, the total number of modifications. Not quite the total. Almost the total. So I'm going to do C times the sum of the number of mods in latest version nodes. Okay, so because we sort of really only care about, we're only changing the latest version, so I really only care about nodes that live in the latest version. What do I mean by this? Well, when I made this new node prime, this becomes the new representation of that node. The old version is dead. We will never change it again. If we're modifying, we will never even look at it again, because now everything points to here. So I don't really care about that node. It's got a ton of mods. But what's nice is that when I create this new node, now the mod list is empty. So I start from scratch, just like reinstalling your operating system. It's a good feeling. And so the potential goes down by 2 times, or I guess C times 2 times P. When I do this change, potential goes down by basically P.
Any constant?
C will be a constant to be determined. Potential, I mean, it could be 1. It depends how you want to define it. I'm going to use the CLRS notion of amortized cost, which is actual cost plus change in potential. And then I need a constant here because I'm measuring a running time versus some combinatorial quantity. So this will be to match some running times that we'll get to. Okay, so what is amortized cost? there's sort of two cases for a modification. There's the cheap case and the not so cheap case. In general, amortized cost, in both cases, is going to be at most, well, first of all, we do some constant work just to like figure out all this stuff, make copies, whatever. So that's some constant time. That's the part that I don't want to try to measure. Then potentially we add a new mod. If we add a mod, that increases the potential by c, because we're just counting mods multiplying by c. So we might get +1 mod. This is going to be an upper bound. We don't always add one, but worst case we always add one, let's say. And then there's this annoying part. And this might happen, might not happen. So then there's a plus, maybe. If this happens, we decrease the potential because we empty out the mods for that node in terms of the latest version. So then we get a negative 2CP change in potential. And then we'd have to pay, I guess, up to P recursions. Because we have to, how many pointers are there to me? Well, at most P of them, because there are at most P back pointers. Or sorry, at most P pointers to any node. Okay? This is kind of a weird, it's not exactly algebra here. I have this thing, recursions. But if you think about how this would expand, all right, this is constant time. That's good. And then if we do this, I'll put a question mark here. It might be here, it might not. If it's not here, fine, constant. If it is here, then this gets expanded into this thing. Okay, it's a weird rate of recurrence, but we get P times whatever is in this right-hand side. Okay, but then there's this minus 2CP. So we're going to get P times 2C here. That's the initial cost. So that will cancel with this. And then we might get another recursion. But every time we get a recursion, all the terms cancel. So it doesn't matter whether this is here or not. You get 0. Which is great, and you're left with the original 2C. So constant. Okay, potential functions are always a little crazy. What's happening here is that, okay, maybe you add a mod, that's cheap, but when we have to do this work and we have to do this recursion, this is up to 2p updates or recursions, we are charging it to the emptying of this node. The number of mods went from 2p down to 0. And so we're just charging this update cost to that modification. So if you like charging schemes, it's much more intuitive. But with charging schemes, it's always a little careful. You have to make sure you're not double charging. Here it's obvious that you're not double charging. Okay, kind of cool and magical. This is a paper by Driscoll, Sarnek, Slater, Tarjan from 1989. So this is very early days of amortization, but they knew how to do it. Question? What happens if you overflow the root? Yeah, I never thought about the root before today, but I think the way to fix the root is just you have one big table that says for a given version, I guess a simple way would be to say not only is a version a number, but it's also a pointer to the root. There we go, pointer machine. So that way you're just always explicitly maintaining the root copy, or the root pointer, because otherwise you're in trouble. So in order to know in order to refer to an old version, you have to have the pointer to that root node. If you want to do it just from a version number, look at the data structure just from a version number, you would need some kind of lookup table, which is outside the pointer machine. So you can do it in a real computer, but pointer machine is not technically allowed. So slightly awkward. No arrays are allowed in pointer machines, in case that wasn't clear. Another question.
Assuming here that all the numbers take constant space to store for all the versions and all, so what if we have really big numbers and a lot of versions? There is
Okay.
login time, right?
In this model, in the pointer machine model, we're assuming that whatever the data is in the items take constant space each. If you want to know about bigger things in here, then refer to future lectures. It's time travel after all. Just go to a future class and then come back. Okay. So we'll get there, but right now we're not thinking about what's in here. Whatever big thing you're trying to store, you reduce it down to constant size things, and then you spread them around nodes of a pointer machine. How you do that, that's up to the data structure. We're just transforming the data structure to be persistent. Okay, you could ask about other models than pointer machines, but we're going to stick to pointer machines here. All right. That was partial persistence. Let's do full persistence. That was too easy. So, same paper does full persistence. That was just a warm-up. Full persistence is actually not that much harder. So full persistence, the theorem is going to be the same. So I'm going to write ditto here, and let me go over to the previous statement of the theorem. So and I'm going to do a mod to this theorem, a little in the spirit of partial and full persistence. Let me tell you what changes about this theorem. We change partial to full. Again, it's going to apply to any pointer machine data structure with a constant number of pointers, call it P, pointing to any node. Now we can make it fully persistent with a constant amortized factor overhead and constant space for each change to the data structure. So exactly the same theorem is possible. We're going to do it in a somewhat different way. A few changes relative to partial persistence, but conceptually similar. We're still going to use mods. We're still going to have multiple nodes representing an original node. But the main annoyance with full persistence compared to partial persistence, we had a linear sequence of versions. Now we have a tree of versions. Trees are annoying to deal with, and it would be really nice when we're talking about all these mods and so on to think about versions as a linear sequence. And it turns out we can do that using a trick called the Euler-Tour. So I'm going to take my tree of versions and linearize it via a tool called Euler-Tour. This is really just a pre- and post-order traversal of the tree. So it's nothing, you've seen it all before. So let me draw a little example. Let's just say the tree of versions is size 3. So this is the original version, and then there were 2 branched versions from there. Then what I'm going to do is do a depth first search of this, or depth first traversal of this tree. So I start at 1, and I'm going to say, okay, I begin 1 by writing an open parenthesis sub 1. In general, the begins are going to be written by open parentheses. The ends are going to be written by closed parentheses. Then I visit 2 for the first time, so I write open parenthesis 2. Then I come back, and this is the last time I visited 2, so I'm going to write close parenthesis 2. I visit 1 again, but it's not the first or the last, so I don't care. Then I come down and I visit, sorry, this is close 2. I'm going to do open 3. This is the first time I visit 3. Then it's also the last time I visit 3. And now it's the last time I visit 1. So this is my parenthesis string that represents this tree of versions. Now, I'm going to interpret this as my timeline, and this is a linear timeline representing this tree of versions. So how do I get this to work? I'm going to say I get a paren sequence, a balanced parenthesis sequence, which is my timeline. So I'm going to think of this as the first time, the second time, the third time, the fourth time, the fifth. This is my sequence of times. And in general, my data structure is going to be working in terms of times, but it's easy to translate between times and versions, which is what I actually care about, is versions. So the idea is that at the time that I'm labeling here as open paren I, we make a change. Meaning all of the changes that are done in version I, like when I went to version 2, those changes are made here in the open parenthesis 2. What about the close parenthesis times? Let me go to here. So the close parenthesis times I'm going to view as unmaking the change, undoing the change. This will be very useful. So I said open parenthesis 2 makes all the changes that were made in 2, and then close parenthesis 2, at this time, conceptually, I'm undoing all of those changes. Why? Because then this linear timeline effectively represents the same thing as this version tree. Because when I look at version 3 over here, it doesn't have any of the changes that were made in version 2. And if I look at the open paren 3 version, or sorry, open paren 3 time in this linear timeline, and I want to know what changes were made here, just like in a regular linear timeline, I can look at all of the past things and accumulate all of those changes. That will be the same thing as in this tree. Because, all the changes in 1 were made, because it's an ancestor. All the changes in 2 were made and then immediately unmade. And so I have the 2 is effectively a no-op here. And then, okay, so that the version that 3 modified was just version 1. So it had this change, and then this change undone. So same thing as being a direct descendant of 1. So just like before, essentially, so over here in our partial persistence solution, we said to read the field of a node at some version, we look at all the mods with version less than or equal to v. This is now going to be all mods with time less than or equal to t, which is going to be the open paren of that version. Okay, so again, we get a linear timeline, and so we can know which mods apply, and everything's happy. There's a slight catch here, which is for how do we number the times? How do we maintain this timeline? With partial persistence, this was easy because we were always adding items at the end of time. And so we could just increment a counter. But the trouble is I can make a new version for 2, which would be inserted right here in the middle of the timeline. So I have to be able to insert kind of in the middle of an array, which in general is hard or it's slow. I need to do this in constant time. Luckily, there's a data structure for this. So we're going to store the times in what's called an order maintenance data structure. This is actually a forward reference to lecture 8. So you can, it's a time travel lecture, you can go to the future, watch that video and come back if you want to know how to do this. But let me tell you just as a black box what that data structure achieves. That's all we'll need for this lecture. So in general, it's a kind of linked list data structure. You have a list of items, ordered list of items. And the update you can do is given an item, insert immediately before or after a specified item in the list. So somehow you've grabbed an item in the list and say, oh, please add right after this one. Just something you can do in a linked list, easy and constant time. But this data structure has an additional query, which is give me the relative order of 2 items. I want to know which one is to the left or which one is to the right. So that's exactly what I need for this timeline, because when I'm trying to decide, does some mod apply to my time, I need to know, is that time less than or equal to some other time? Comparing times is all I need to be able to do with times. And I need to be able to create a new time in the middle. So if I want to update version I, So version is always going to, word version I'm going to use to refer to nodes in this tree, in the version tree, and times I'm going to use to represent the parens, or the linearized time. So this is kind of repetitive, but whenever I want to do an update, I'm going to do 2 mods to the data structure. One at a new time, open paren I prime, I'll call it, and close paren I prime. And they will be inserted right after open paren I. So version I is the one I'm modifying. I'm calling the new version that I make I prime, just to give it a name. So I find the open paren I in the timeline, and then I insert this after it, and then I insert this after that. So what that looks like in the tree is that I have version I. It has some existing children here, and then I'm adding a new child on the left, which is called I prime. Because the open parenthesis I is right here. If I insert something right after it, that will be a new leaf version right after I. So that's what it does. What does this mod do? This is going to do the change, and this mod is going to undo the change. And so I preserve this linear timeline where open paren makes a change, close paren undoes that same change. And so these nodes will not be affected because they see in the left of the timeline, they see this change made and then unmade. So these guys all get version I, as they should. Okay, so we preserve all the invariants by doing this. This was a bunch of work, but the nice thing is now we can just think about linear timelines. And because of our order maintenance data structure, we can just treat these as magical numbers that we can compare, and we can insert one wherever. And so we don't need to worry about that. What we need to worry about is things like back pointers, because this is going to change a lot as well. With back pointers in the partial persistence analysis, we used that we only cared about the latest version. That is no longer true. There are many latest versions. I mean, every version is modifiable with full persistence. I can modify I again. I can modify any of these children. Everything is active at all times. So we can no longer do back pointers just for latest version. We just need to store back pointers. Every pointer has to have a corresponding back pointer at all times. So at this point, pointers are basically symmetric. You could call them forward pointers and back pointers. And internally, there's a difference. The data structure is actually using the forward pointers, and we're maintaining the back pointers automatically. But effectively, every pointer is just bidirectional. So we don't get any nice benefit here. As a result, we're going to need a few more mods per node. It's going to be, at most, 2 times d plus p plus 1. Remember, d is the out degree of a node, p is the in degree. These are now symmetric, so d plus p is just the number of pointers in the node. And then we're going to add 1 and multiply by 2. It's roughly like we had before. I've just also got a plus 1 here. That's how many mods we're going to store per node. So the nodes are going to look the same. There's a version over here, which I'm going to call the, got a name for this, the base version. Just to have a word to distinguish it from the mods. And now this is going to be 2 times d plus p plus 1. Here we're storing the forward pointers and the backward pointers and any other data items values. But the total size here is d plus p. Okay, so otherwise the data structure is going to be the same. And the reading algorithm is just the same. Because we've linearized versions, we can do just compare the times using our order maintenance data structure, and we know which mods apply. And so we can reconstruct what this node looks like at each time that it represents. The big question is, how do we maintain the back pointers, basically? Because, again, nodes are moving. We've got to update those back pointers. This is going to propagate in general, and so we're going to have to do a harder amortization than this argument. So let's go to the update algorithm. And I think at this point, I'm going to erase instead of using a mod. This is, I guess, a metaphor for the data structure. For a while, as long as there's a small number of changes, you just cross things out and write the new version. But once the blackboard or the node has changed too much, then you just start over and make a new node. In my case, I have a finite number of blackboards. But in general, you should be remembering what was here on the board before to mimic full persistence. All right, so we want to modify a node. So we're going to add a mod, just like before. So I'm just going to phrase this algorithm a little bit differently. In that I'm going to allow the node to temporarily overflow, and then I'm going to tell you how to split a node when it overflows. Okay, so right now I might have, in all cases, I'm going to add a mod, but then I may have too many mods in the node, and then I'll fix it. Slightly different from my phrasing before. Cool. So that's an update, and I'll view update as taking constant time. But whenever a node overflows, so this means that it has 2 times d plus p plus 1 mods. So this is like 2d plus 2p plus 3 mods, just one more than. I'm constantly adding mods. At some point, nodes will overflow. Immediately, whenever any node overflows, I'm going to call this subroutine that I'm about to say. The subroutine conceptually is going to split the node into 2 nodes that are each roughly half full. Okay, the spirit here is like in B trees. If you know B trees, whenever you have a node and it overflows, you split it into 2 halves of equal size. So it's like a B tree node. There's no tree, obviously, but it's like one node of a B tree. Slightly different, but conceptually that's what's going on. Okay, so how do we do the split? This is not obvious. What we're going to do, first of all, is find the middle time. T star. So I'm going to draw a picture. Conceptually, take one of these nodes with mods in it. It's got this huge number of mods, and sort them by time. Time is linear, so let's sort them by time. So this is the mod with the earliest time. This is the mod with the latest time. Total number here is 2 times d plus p plus 1 plus 1. If I sort by time, some of these mods will have the same time. Maybe the first chunk here is all with that initial time. I'm drawing vertical lines whenever I have a change in time among these mods. And then all I'm going to do is take the middle one. So there's some t star, which is the median time. Would probably be a better word here. Let's call it the median time among all of the mods in this node. Call that t star. And I'm going to treat all of these mods that use that same time t star in the same way. That's why I drew these vertical lines to separate the different times. So that's the median time t star. So now I'm ready to define what the split does. I say I split into 2 nodes, but in fact I want to minimize motion as much as possible. So one node I'm just going to leave where it is, but I'm going to change what's in it, and then I'm going to make a new node. So there's the old node. It's going to keep some of the mods. It's going to keep mods at time less than t star, strictly less than. So that's these guys. Those remain in the old node. So the old node had all of these mods. I'm going to throw away all of the mods from t star onward in that node. And then the new node, which, just like partial persistence, I'm going to call node prime, it's going to keep mods at time greater than t star. Greater than, not equal to. This is key. This is what makes the analysis work. So, so we have, this is the old, and this is the new. So in the new node, we have these mods stored. In the old node, we have these mods stored. What about the mods at time t star? I'm going to throw them away. How do I do that? By updating the base version for node prime. So the base version of node prime is going to be equal to the old base version with all of the mods at less than or equal to t star applied. Okay, so this is the one place where I have equality. That's the one place where the mods of t star are actually not being lost, is in the base version. So we have our old node. It has some old base version and too many mods. We extract all the later mods from that version, but otherwise leave that node alone. We make a new node prime whose base version is like this one, but it has all of these mods applied from the old version to the end of t star. That's here. And then the mods that are stored in this node, so this is node prime. These mods are the latter ones here strictly after t star. So basically we get to eat up t star here by storing it in the base version, which in particular decreases the total number of mods by at least one. Maybe there are several mods with time t star, but there's at least one mod with time t star because it's a median, it's an existing thing. So the total number of mods is going to go down from this value to one less. In other words, this chunk that goes in the old node and this chunk of mods that goes in the new node will each have size or length at most d plus p plus 1. So we just say both of these are at most d plus p plus 1 because this plus 1 disappeared from annihilating t star, which left us with this. We're splitting in half, and so this 2 disappears. Each half will have at most d plus p plus 1 mods. Okay, that's going to be important for the amortization, which is almost the next thing to say. But there's one other thing we need to do. Let me do it over here. We've linearized the timeline, so I don't need to keep track of that anymore. So the thing that's left to do is update the reverse pointers. Okay, I said every pointer has to be bidirectional. We have to maintain these back pointers everywhere now. Every back pointer also has its reverse version, which is the forward pointer. Every forward pointer has a reverse version, which is the backward pointer. Whenever we move a node, and here we're splitting a node into 2 parts, and so in some versions it's moving, and sometimes it's moving, we need to update pointers to that node. Now, there are 2 kinds of pointers to that node. This is a little bit subtle, but it's very important to get the analysis right. In general, I'm going to call them the reverse of a pointer. It's the reverse of a forward pointer is a backward pointer, and vice versa. So type 1 of pointer so every pointer has a reverse pointer. And if the reverse pointer is in the base version, I think at this point I need to draw the general diagram of what's going on. So we have we used to have a node here, which had some base version. and then an overflowing group of mods, and we split it into the old node, which now has half of the mods, strictly less than half, and into a node prime, which also has half of the nodes. And then we also updated the base version of node prime. So the first thing I'm interested in are these pointers, I'll draw them in red, that come out of the base version. Okay? So for each such pointer, there's a reverse pointer which needs to be updated because it used to point to node, now it has to point to node prime. Okay, these are the hard ones. These ones I'm going to use mods and recursively doing splits to update them. So that's it. So what's good about them is we know there's at most d plus p pointers in every node. Again, merging the forward and backward pointers, d forward, p backward. But there's at most d plus p pointers in this base version. For each of them, we add a mod to the other node. In other words, we recursively do a modify. And then if that node is overflowing, we recursively do a split. Okay? So that's the recursion. There's another type of pointer, which are these ones. Those ones I claim are actually easier to deal with. And we're going to directly update them. Again, we only care about pointers in node prime. The ones in node haven't changed. Nothing needs to move. Or nothing did move. But node prime is what changed. So we worry about the ones in the base version, and we worry about the ones in the mods. But I claim the ones in the mods can be updated directly in constant time. Why? Because these mods that are in node prime correspond in the old world to, before we did the split, to these mods. All of these mods are at time strictly greater than t star. That's what we said here. Node prime gets the mods that happen at time strictly greater than t star. That's interesting because node essentially is representing all the versions of this node before t star, and node prime is representing this node at times greater than or equal to t star. Now all of these mods happened at time strictly greater than t star, which means any pointer that comes out of here, its reverse pointer, because we always change pointers in pairs, this reverse pointer will always have a time that it pointed to strictly greater than t star, which means this reverse pointer doesn't care anymore about node. It only cares about node prime. Whenever you're following this particular pointer, it will always want to go to node prime because node prime represents all those versions. So we can just directly update, just go in there, modify the cell that's in that node, modify the pointer. You don't have to do a recursive update. Hopefully that's clear. This is the heart of why this thing can be efficient. Otherwise, you just keep changing pointers and you never finish. You need some situation where you can just directly change a pointer with no recursion. Otherwise, you'll just infinitely recurse. So this is essential to why full persistence works. But we still do have this recursive case. We're doing a ton of recursive mods here. To analyze this, we need to use a potential function again, just like before, but a different potential function. So let's go back to amortized analysis. So, new potential function. It's again going to have a constant c in front. I'm going to sum over each node. I kind of want to count the number of mods in the node, but let's be a little bit more careful than that. This is a common trick for things like B trees, which is in general, when I split a node and I make two half-full nodes, in steady state, after things have run for a while, I will never have an empty node in this view. With partial persistence, I got an empty node every time I created a new one. But with full persistence, every time I do a split, I have a node that's half full. So at steady state, all the nodes are between half and 100% full. So what I'd like to do in the potential function is just forget about that first half. Don't count the first half of the node. Only count in the second half of the node how many of these get filled up. Okay, so that's what this is saying. In the second half, in other words, we don't count the first d plus p plus 1 mods. We just count from there up to the end, 2 times d plus p plus 1 mods. So don't count the first d plus p plus 1 mods. Okay, and then I do that for each node separately and add them up and multiply by c for a constant c to be chosen. Okay, so under this potential function, we're going to analyze 2 things. First is the cost of an update. Okay, read is just constant time. You just look at the node. But to modify, well, we add a mod. So this takes time, and it also potentially increases the potential. Potentially increases the potential. It might increase the potential. So an update or modification to node.field has an amortized cost of c plus c. This is like what we did with partial persistence. The first c is like the running time. We're using time for other things, so I'll just call this the work of the algorithm to do this, to add the mod to the structure. And then the other c is because the potential goes up by, it might not go up. If you're adding an early mod that's in the first half of the node, then you won't pay anything. But if it's in the second half of that node, worst case, you increase by c. Okay, no big deal. This is constant. Okay, this is ignoring the split costs. Okay, when you actually, if you code this up, in this algorithm you would say, if you're now overflowing, you'd call split. Okay, but I'm going to think of this as a background process. And I won't attribute the cost of splitting to the cost of modifying, just because I want to analyze the split separately instead of using recursion, because that was messy with the partial persistence. Okay, so that was the analysis of update ignoring split. Now let's analyze the cost of split ignoring update. And then we add them together, we'll get the total cost. So what happens in a split? We have this picture. So again, we're ignoring the first half of the node. This is d plus p plus 1. It's d plus p plus 1. Before we actually do the update, we haven't added the extra plus 1 guy, extra mod. So before we do this split, we have potential here, which is like d plus p plus 1. And it disappears. So potential of that node goes down by c times d plus p plus 1 in this node. Or I guess in node and node prime, because both of these, after we do the split, are empty in the second half. So these guys both have 0 potential, whereas this one has potential d plus p plus 1. Maybe even plus 2, but I don't need that for this analysis. Okay, so great. Our potential went down because we had a full node. Now we have 2 half-full nodes. This counts as d plus p plus 1. This counts as 0. This counts as 0. So that's a decrease in potential. Unfortunately, potential also goes up for a different reason, namely these. When we do a split, because the node moved, we had to do these mods to update the location of that node in certain timelines. But we knew there was only d plus p of them, because it only corresponded to the base version of node prime. So we increase the potential d plus p times c. So potential goes up by c times d plus p. This is for the mods. And so the actual change of potential is the sum of these two changes. So in aggregate, we get that total potential goes down by c. Nice. That's good. We set c to the the cost of a split, the actual cost, let's say. How long does it take to find the median? This is all a constant size thing, but you make the new node. That takes constant work. Okay, you set c to be that constant amount of work, then the amortized cost of a split is 0. Amortized cost is actual cost plus change of potential. But potential goes down by c every time you do a split, which pays for the split. So if you think of the splits as a separate process, they're completely free. And so then it doesn't matter if you add them into an update. Okay? So amortized cost of split is 0. Cool. So that's what I wanted to say about full persistence. Once you know splits are free, then updates, in an amortized sense, updates have constant amortized cost. And so we get this theorem, constant amortized factor overhead. Of course, we're also spending a constant amount of space for each change that we do in order to write down the mod. We have to pay that. But we get full persistence at any point in machine data structure with bounded in and out degree. Any questions? Okay, one last thing I want to say. It's mostly a natural question is, we have this amortization in the overhead, but if you have a data structure that runs really fast per operation, you'd maybe like to preserve the worst case time as well. And it turns out so when can we get worst case? And the answer turns out to be that for partial persistence, you can get constant worst case factor overhead. This is a result a decade later by Geert Brodel. But for full persistence, which is what's currently written in red here, so maybe actually I'll write worst case in white. In the red case, which is the full persistence, there's a question mark. This is open. Can you achieve worst case factor overhead with the full persistence that we just saw? We don't know, but for partial persistence, it's possible. Okay, so an example of an open problem in the field. And that's it for full persistence. So let's go to over here. It's full persistence. Last topic is confluent persistence. Lots of things go out the window with confluent persistence. In particular, your versions are now a DAG. In DAG, it's a lot harder to linearize a DAG. Trees are not that far from paths, but DAGs are quite far from paths, unfortunately. But that's not all that goes wrong. Let me first tell you the kind of end effect as a user. Imagine you have a data structure. It maintains, think of it as a list, I guess, which is a list of characters in your document. You're using VI or Word, your favorite, whatever. It's a text editor. You've got a string of words. And now you like to do things like copy and paste. It's a nice operation. So you select an interval of the string, and you copy it, and then you paste it somewhere else. So now you've got 2 copies of that string. This is, in some sense, what you might call a confluent operation, because, maybe a cleaner way to think of it is the following. You have your string. Now I have an operation which is split it. So now I have 2 strings. Okay, now I have an operation which is split it. Now I have 3 strings. Okay, now I have an operation which is concatenate. So I can, for example, reconstruct the original string. Well, actually, I have the original string. No biggie. Let's say, because I have all versions, I never lose them. So now, instead, I'm going to cut the string here, let's say. So now I have this and this. And now I can do things like concatenate from here to here to here. And I will get this plus this plus this. Okay, this guy moved here. So that's a copy-paste operation with a constant number of splits and concatenates. I could also do cut and paste. With confluence, I can do crazy cuts and pastes in all sorts of ways. So what? Well, the so what is I can actually double the size of my data structure in a constant number of operations. I can take, for example, the entire string and concatenate it to itself. That will double the number of characters, number of elements in there. I can do that again and again and again. So in U updates, I can potentially get a data structure size 2 to the U. Kind of nifty. I think this is why confluence is cool. It's also why it's hard. So not a big surprise, but here we go. In that case, the version DAG, just for reference, looks like this. You're taking the same version, combining it. So here I'm assuming I have a concatenate operation. And so the effect here, every time I do this, I double the size. All right, what do I want to say about confluent persistence? All right, let me start with the most general result, which is by Fiat and Kaplan in 2003. They define a notion called effective depth of a version. Let me just write it down. It's kind of like if you took this DAG and expanded it out to be a tree of all possible paths. Right? Instead of pointing to the same node, you could just duplicate that node and then have pointers left and right. Okay, so if I did that, of course, the size grows exponentially. It explicitly represents the size of my data structure. At the bottom, if I have U things, I'm going to have 2 to the U leaves at the bottom. So, but then I can easily measure the number of paths from the root to the same version. At the bottom, I still label it, oh, those are all V. They're all the same version down there. So exponential number of paths. If I take log, I get what I call effective depth. It's like if you somehow could rebalance that tree, this is the best you could hope to do. It's not really a lower bound, but it's a number. It's a thing. Okay. Then the result they achieve is that the overhead is log the number of updates plus, this is a multiplicative overhead. So you take your running time, you multiply it by this. And this is a time and a space overhead. So maximum effective depth of all versions, maybe even sum of effective depths, but let's just say max to be safe. If you sum over all the operations, this is per operation. You pay basically the effective depth of that operation as a factor. Now, the annoying thing is if you have this kind of setup where the size grew exponentially, then the number of paths is exponential, log of the number of paths is linear in U, and so this factor could be as much as U, linear slowdown. Now, Fiat and Kaplan argue linear slowdown is not that bad because if you weren't even persistent, if you did this in the naive way of just recopying the data, you were actually spending exponential time to build the final data structure. It has exponential size. Just to represent it explicitly requires exponential time. So losing a linear factor to do U operations is now U squared time instead of 2 to the U. So it's a big improvement to do this. The downside of this approach is that even if you have version DAG that looks like this, even if the size of the data structure is staying normal, staying linear. So this potentially you could be doubling the size, but we don't know what this merge operation is. Maybe it just throws away one of the versions or does something. Somehow takes half the nodes from one side, half the nodes from the other side. Maybe these operations do preserve size. Then there's no great reason why it should be a linear slowdown, but it is. Okay, so it's somewhere, it's all right, but not great. And it's the best general result we know. They also prove a lower bound. So lower bound is sum of effective depths, total bits of space. Okay, what does this mean? So even if this is not happening, the number of bits of space you need, in the worst case, this does not apply to every data structure. That's one catch. They give a specific data structure where you need this much space. So it's similar to this kind of picture. Won't go into the details. And you need this much space. Now this is kind of bad because if there's U operations and each of these is U, that's U squared space. So we actually need a factor U blow up in space, looks like. But to be more precise, what this means is that you need omega E of V space and therefore time overhead per update if, this is not written in the paper, queries are free. Implicit here, they just want to slow down and increase space for the updates you do, which is pretty natural. Normally you think of queries as not increasing space. But in order to construct this lower bound, they actually do this many queries. So they do E of V queries and then one update. And they say, oh, well, the space had to go up by an extra E of V. So if you only charge updates for the space, then yes, you have to lose potentially a linear factor, this effective depth, potentially U. But if you also charge the queries, it's still constant in their example. So open question, for confluent persistence, can you achieve constant everything? Constant time and space overheads, multiplicative factor, per operation, both updates and queries. So if you charge the queries, potentially you could get constant everything. This is a relatively new realization. And no one knows how to do this yet. Nice challenge. I think maybe we'll work on that in our first problem session. I would like to. Questions about that result? I'm not going to prove the result, but it is fancy rebalancing of those kinds of pictures to get this log. There are other results I'd like to tell you about. So brand new result. That was from 2003. This is from 2012. No, 11, sorry. It's SOTA, which is in January, so a little confusing. Is it 11? Maybe 12. Actually, now I'm not sure. It's February already, right? A January, either this year or last year. It's not as general a transformation. It's only going to hold in what's called a disjoint case, but it gets a very good bound. Not quite constant, but logarithmic. Okay, logarithmic would also be nice. Or log n, whatever n is. So pick your favorite n. Number of operations, say. Okay. If you assume that confluent operations are performed only on two versions with no shared nodes. Okay, this would be a way to forbid this kind of behavior where I concatenate the data structure with itself. All the nodes are common. If I guarantee that maybe I slice this up, slice it, dice it, whatever, and then remerge them in some other order, but I never use two copies of the same piece, that would be a valid confluent operation over here. So this is quite a strong restriction that you're not allowed. It won't even, if you try to, who knows what happens. Behavior is undefined. So it won't tell you, oh, those two versions have this node in common. You've got to make a second copy of it. So somehow you have to guarantee that confluent operations never overlap, but they can be reordered. Then you can get order log n overhead. N is the number of operations. I have a sketch of a proof of this, but not very much time to talk about it. All right, let me give you a quick picture. In general, the versions form a DAG. But if you make this assumption, and you look at a single node, and look at all the versions where that node appears, that is a tree, because you're not allowed to remerge versions that have the same node. So while the big picture is a DAG, the small picture of a single guy is some tree. Okay, I'm drawing all these wiggly lines because there are all these versions where the node isn't changing. This is the entire version DAG. And then some of these nodes, some of these versions, I should say, that node that we're thinking about changes. Okay, whenever it branches, that's probably because the actual node changed, maybe. I don't know. Anyway, there are some dots here where the version changed. Some of the leaves, maybe it changed. Maybe some of them hasn't yet. In fact, let's see. Here, where it's changed, it could be that we destroyed the node. Maybe it's gone from the actual data structure. But there still may be versions down here. There could be, it's not really a tree, it's a whole DAG of stuff down there. So that's kind of ugly. Whenever the node still exists, I guess that is an actual leaf of the DAG, so those are okay. But as soon as I maybe delete that node, then there can be a whole subtree down there. Okay, so now if you look at an arbitrary version, so what we're thinking about is how to implement reading, let's say. Reading and writing are more or less the same. I give you a version, I give you a node, and I give you a field. I want to know what is the value of that field, that node, at that version. So now where could a version fall? Well, it has to be in this subtree because the node has to exist. And then it's maybe a pointer. The pointer could be to another node, which also has this kind of picture. They could be overlapping trees. In general, there are three cases. Either you're lucky, and the version you're talking about is a version where the node was changed. In that case, the data is just stored right there. That's easy. So you can just say, oh, how did the node change? Oh, that's what the field is. OK, follow the pointer. A slightly harder case is it's a version in between two such changes, and maybe these are not updates. So I need to know I sort of want to know what was the previous version where this node changed in constant time. It can be done, not constant time, actually, logarithmic time, using a data structure called link cut trees. Another fun black box for now, which we will cover in lecture 19, far in the future. Okay. Then, well, that's one case. There's also the version where maybe a version is down here in a subtree. I guess then the node didn't exist. But, well, all these things can happen, and that's even harder. It's messy. They use another trick, which is called fractional cascading, which I'm not even going to try to describe what it means, but it's got a very cool name. Because we'll be covering it in lecture 3, so stay tuned for that. I'm not going to say how it applies to this setting, but it's a necessary step in here. In the remaining 0 minutes, let me tell you a little bit about functional data structures. So, beauty of time travel. Functional. I just want to give you some examples of things that can be done functionally. There's a whole book about functional data structures by Okazaki. That's pretty cool. A simple example is balanced BSTs. So if you just want to get log n time for everything, you can do that functionally. It's actually really easy. You pick your favorite balanced BST, like red-black trees. You implement it top-down, so you never follow parent pointers, so you don't need parent pointers. So then as you make changes down the tree, you just copy. It's called path copying. Whenever you're about to make a change, make a copy of that node. So you end up changing you copy all the change nodes and all their ancestors. There's only log n of them, so it takes log n time. Clear? Easy. It's a nice technique. Sometimes path copying is very useful, like link cut trees, for example, can be made functional. You don't know what they are, but they're basically a balanced BST, and you can make them functional. We use that in a paper. All right, DEX. These are doubly ended queues, so it's like a stack and a queue and everything. You can insert and delete from the beginning and the end. People start to know what these are now, because Python calls them that. But you can also do concatenation with DEX in constant time per operation. This is cool. DEX are not very hard to make functional, but you can do DEX, and you can concatenate them like we were doing in the figure that's right behind this board. Constant time. Split is a little harder. That's actually one of my open problems. Can you do lists with split and concatenate in constant time? Functionally or confluently, persistently, or whatever. Another example, you can do a mix of the two. You can get log n search in constant time DEC operations, is you can do tries. So a trie is a tree with a fixed topology. Think of it as a directory tree. So maybe you're using subversion. Subversion has time travel operations. You can copy an entire subtree from one version and stick it into a new version, another version. So you get a version DAG. It's a confluently persistent data structure. Not implemented optimally, because we don't necessarily know how. But there's one paper, this actually came from the open problem session of this class 4 years ago, I think. It's with Erik Price and Stefan Langerman. You can get very good results. I won't write them down because it takes a while. Basically log the degree of the node's factor and get functional, and you can be even fancier and get slightly better bounds like log the degree and get confluently persistent with various tricks, including using all of these data structures. So if you want to implement subversion optimally, that is known how to be done, but hasn't actually been done yet because there are those pesky constant factors. I think that's all. What is known about functional is there's a log n separation. You can be log n away from the best. That's the worst separation known between functional and just a regular old data structure. It'd be nice to improve that. Lots of open problems here. Maybe we'll work on them next time.